Okay, so this is Lab 2, Motion of a Falling Object for Physics 2211. The overall purpose of this lab was to find the relationship between different models representing an object falling from rest in terms of experimental data, the computational model with drag incorporated, and the computational model without drag incorporated. The implications of this experiment and the importance of the subsequent results are to understand and analyze the models that both account for the effect of drag and neglect it. The main concepts and equations that were implemented in the computations for this lab were mostly depending on the fundamentals of Newton's second law, or the momentum principle, which uses the relationship between a system and its surroundings to analyze its motion by using the net force, by using the formula mass times velocity final equals mass times velocity initial plus net force times the change in time. In this experiment, there is a non-zero net force present. The two forces acting on the plastic bottle that were dropped from rest are gravitational force and drag. Gravitational force is the force exerted by the Earth in the negative y direction, which can be seen in the diagram to the right, and is given by the equation mass times gravity times the unit vector. Drag, also known as air resistance, is the force that acts in opposition to the gravity in the positive y direction and is given by the proportionality constant times the magnitude of the velocity squared times a unit vector in the opposite direction of the velocity at that instant, where b is calculated numerically by choosing different values between 0 and 1 until a graph that closely depicts the experimental graph is found. Here you can see I had a friend drop an empty plastic Powerade bottle from rest. The center of mass is tracked throughout the length of the fall, and the fall lasted 0.6 seconds. As the object was dropped, the position versus time graph is displayed in the top right corner of the screen. Using the data that tracker outputted, a graphical analysis was able to be created. Here you can see a graphical representation of the data that was found, where the blue line represents the experimental data recorded from the tracker video, the gray line represents the computer model with drag incorporated, and the orange line represents the computational model with drag not accounted for. It is evident that the model without drag overestimated the velocity, whereas the model incorporating drag was closer to the experimental model, but not completely perfect, as there were likely some other factors that played a role in the fall of the object. In order to analyze the data for this experiment and create accurate models, two different codes were created. The first code is one that incorporated drag, while the second code did not account for drag and was only representative of the gravitational force. In both codes, there were some conditions and formulas that were needed. The mass of the object was found to be 0.03185 kilograms. The initial position and velocity vectors were both at the 0 position, as the starting point on the tracker app was set to be at 0.0 for the center of mass of the bottle. Additionally, the time step for both was changed to be 0.033 seconds, which was found by the total elapsed time divided by the number of frames. The time it was run was adjusted to be 0.6 seconds based on the length of the video that was analyzed and when the bottle hit the ground. The velocity and ball position equations were edited to incorporate the net force and elapsed time. Here you can see a video of the computational display produced by this code. For the code without drag incorporated, only the force of gravity is accounted for using the formula mass times gravity times j hat, so the net force is only equal to that of the gravitational force. Once again, you can see the computational output produced by the code that neglected drag. Terminal velocity is when the magnitude of the force of drag is equal to the magnitude of the force of gravity. Since these are the only two forces being accounted for in this experiment, the net force is therefore 0 at this point. To answer some questions about how terminal velocity played a role in this object's falling, in the experimental data, no terminal velocity is reached. From the graph on the previous slide, it can be seen that the velocity is still changing when the time hits 0.6 seconds or when the object hits the floor. It did not fall for a long enough time to reach its terminal velocity or from a high enough height. In the graph displayed here, 4 different theoretical curves are plotted. If no drag was incorporated, no terminal velocity could ever be reached and it would theoretically fall forever. For the curve in blue, drag is incorporated for the same conditions as in the experiment, except allowing it to be computationally run for a longer amount of time. As can be seen, a terminal velocity is reached at approximately -7 meters per second. The gray curve represents a fall with a small initial velocity, meaning an initial velocity less than the terminal velocity. The terminal velocity still lows out at about -7 meters per second again. The yellow curve represents an initial velocity of greater than that of the terminal velocity found in the other steps, and it can be seen that the object actually slows down to reach that terminal velocity once again. Therefore, changing the initial velocity by throwing the object or providing a force at the beginning will not change the terminal velocity at all, as it is not affected by any sort of initial conditions. Overall, the model without drag was an overrepresentation of the actual velocity because not accounting for drag gives a greater net force overall and therefore a greater acceleration. Additionally, the model that did incorporate drag was not a complete match to the experimental data, which was likely due to the fact that the bottle wavered slightly in the air as it fell, meaning the drag constant was not constant throughout the entirety of the fall. The results of this experimental analysis are important to understand an object's motion as it falls, to create models that can be altered to predict the velocity and position of objects at different points. That is all for Lab 2 for Physics 2211. Thanks so much for watching.